Hello, everybody. Good morning. This is Math 145, day 7. Welcome to my attic. So this is what we're going to do for online lectures. I'm going to post video clips like this one. And instead of writing on paper, I'm writing on this tablet. And you'll get used to it. So we have some leftovers from lesson 6. Recall that we had said that two functions are inverses of each other, say f and g, their functions are inverses of each other if f of g of x is x and g of f of x is x. For every value x in the domain of g for the first equation, so every legal input value for the first equation, and in the second equation we want this for every x in the domain of f. Let's do some examples. Y is f of x equal to 2x minus 3. Find the inverse of f of x. And here's the mantra. The way to go about this that I want you to remember, it's solve and switch. Solve and switch. Which means take that equation, y is 2x minus 3, and solve it for x. That's not too hard. We add 3 to both sides. So we get y plus 3 is 2x. Divide by 2. So we got 1/2 times y plus 3 is equal to x, and we have solved it for x. Second part, switch the two variables, that is, switch x and y, and we get y is 1/2 times x plus 3. And that'll be our formula for the inverse, g of x. That's all there is to it. Solve and switch. By the way, you can do this the other way around. You can do switch and solve, but I think the solve and switch is more intuitive because it really doesn't matter what label, what name we give to the input on the output variable, at least from one viewpoint. The function g is the operation of multiplying your input, adding 3 to your input variable and then multiplying by 1/2. The function f takes the input and multiplies it by 2 and then subtracts 3. Whatever that input variable is called, or if it's a value, if it's 5, that's what you do to the 5. Okay, so think of the function as an operation, and then the inverse function is that operation which reverses the effect of the original. So it takes the output and comes back with the original input. And that's the reason why this method is the right method. The switching part is just because we typically like our input variable to be called x and the output variable to be called y, and so that's why we do that. Sometimes you want to plot those function and inverse in the same coordinate system, so the input variable and output variable have to have the same name, and then it's really obligatory. So let's say for those problems, find the inverse, we really want the input and output variable to have the same names as the original. And then you need to do that switching. But the computation wasn't too hard. Let me give you one example to do yourself. What if your function is y equal to 2x plus 1 divided by 4x minus 3? You take some pencil and paper, take a crack at it, and we're going to do that. I'll check on you if you did that right in the lesson time, in the lecture time on Monday. But take a crack at it. It's a little harder, but it's still the same mantra. Solve that equation for x and then switch. I'm going to do a third example, which is different in that computation is easier and there's an unexpected difficulty. Y is x squared. And here we hit on a difficulty. By default, our domain is every legal input value. So that's just from negative infinity to positive infinity. And here I might as well tell you the inverse for this function does not exist. This is possible. How can we tell why? Does it not exist? Think of, again, the inverse as a function that reverses the effect. So it takes the output, x squared, and wants to recover the value x from that. And you got two choices, okay? You got the square root of y or the negative square root of y, and you don't know which was the input, right? Except if it's 0, then obviously there's only one choice, but for every other value, there's two choices. Given y, there's always two choices, and that would be the square root of y or the negative square root of y. Except if y is actually 0. That's one exception. But usually you have two choices, you can't find that x. There's no way of telling if you only know the x squared, which is the y. So that's the reason why there is no inverse for this example. And then let's just slightly change it or fix it. And let's just say we use the domain from 0 to infinity. Infinity always open, that end. We can include the 0, and the problem goes away. So given y, we can solve that equation for x, and we get x is the square root of y. That's the solving part, switch. We get y is the square root of x. That's my formula for g of x for my inverse, and everything's fine. Because with that domain, I knew the x, the input, had to be non-negative. There's only one choice. And just for the heck of it, same function, y is x squared. Take the domain from negative infinity open to 0. And we can solve this given y. X is the negative square root of y. This time we know x was negative or 0. So we take the negative square root. And then switch. Y is negative square root x. That is my formula for the inverse. Okay, so that solved one example. It helps to connect the whole thing to graphs. Graphs of a function and its inverse. Let me sketch the graph of y is x squared. Make it a little neater. So something like this. Of course, at 0, it's 0, and it goes up. Here it comes down. Mirror image, because it's an even function. And the fact that for every given y, that's all the points with a given y value, that's a horizontal line. There are two possible x values. That's reflected in the fact that the horizontal line, y is equal to 3, intersects the graph of my function in 2 points. Right, there's here and there's there. And those correspond to the two x values, square root 3, comma 2, and then there's negative square root 3, comma 3 on the graph. So that's a graphical reason why there is no inverse for this whole function when we go for the whole number line. And the whole idea here is called the horizontal line test. This graph fails the horizontal line test because there's more than 1 point of intersection with the graph. Okay, and then when we took the artificial domain from 0 to infinity, let me just sketch the right half of this whole picture. So only that part. That's my domain. That's my graph. I forget about the left half. And then my horizontal lines only have 1 point of intersection. No matter where you put that horizontal line, you only get 1 point of intersection. At least not 2. If you go below the x-axis, you would get 0 points of intersection. That's allowed. But At least we can't get 2 or more. And then for every y is x squared, there's only one possible value of x. Horizontal line, oops, test. Success. And similarly, if you just take the left half of your graph, you would also just get one point of intersection with any horizontal line that you pick in the upper half plane, not 2. And in success, there is an inverse. How do we find a formula for that inverse? Well, that's ridiculously easy. I mean, that's the square root of y, and then you switch, and it's the square root of x. But while we're at it, let's plot that graph of y is square root of x. And I'm going to make a new picture not to crowd this. So like this, 1, 2, going up and up. Those 2 points on it, and you connect them as best you can, because we're going by hand here. What's the graph of y is the square root of x? I expect you've all seen that graph, or you can do it on your calculator. Try to figure out how to do it on your calculator, plotting 2 functions in the same coordinate system. So the square root of x goes through that point as well. But when x is 4, you just reach y is 2, about here. So square root of x looks roughly like that. What's going on? What's the relationship between those 2 graphs? And the answer is, one is a mirror image of the other. So as an example, look at the point on the graph of the original, that's y is x squared. We got the point x is 2, y is 4. And the mirror image is the point 4, 2 on the graph of y is square root x, the inverse. Notice how the values are switched. That's exactly because we switched the x and the y. Solving an equation for a variable did not change the relationship between x and y. Not switching them, geometrically, that changes, and it changes the point 2, 4 to the point 4, 2. So you get a mirror image with the axis of symmetry being that 45-degree line with the equation y is x. So here is 45 degrees. And for example, the point 1, 1 is on the line, so when you mirror it, it stays where it is. And this is not just true for this example. Your turn, you graph y is 2x minus 3, and the inverse y is 1/2 times x plus 3 in the same coordinate system, and you should get 2 straight lines which are mirror images of each other about the same 45-degree slanted straight line, the bisector of the first quadrant. Okay. Remember that horizontal line test, so you can graphically determine whether an inverse exists or not. Another thing that It's related to the horizontal line test. An inverse of f of x on a given domain D exists if f of x is an increasing function on that domain. Back to the last example here, y is x squared, that's an increasing function on the domain which is from 0 to infinity. It's increasing there, okay? Because, well, you can think about that. This implies it will pass the horizontal line test. However, it also will exist if f of x is decreasing on the whole domain. And that will be the example where I pick the left half of this parabola. I pick y is x squared and the domain from negative infinity to 0. Then your function is always decreasing, passes the horizontal line test, and an inverse exists, or as left half. You can do that in your head, right? Just imagine the left half. Right half is gone, erased, destroyed, and then your function is always decreasing. But inverse does not exist if it's mixed. At least, okay, it's not guaranteed to exist if it's mixed. Sometimes decreasing, sometimes increasing. That if your function doesn't make a jump, then you can actually guarantee if it's sometimes increasing, sometimes decreasing, then there will not be an inverse. Right. That's the first half. That's the rest of lesson 6. And I'll stop here and do another video clip for the beginning of lesson 7.